and I ended up submitting a kernel patch. The patch was completely wrong and people gave me feedback and eventually the patch got in. But that's how I got involved in the kernel development, and it opened up my eyes in terms of it's possible to do kernel development and I can work on something that then gets installed in millions of devices and everybody can use it. I also truly believed open source would improve the ecosystem.
You are listening to the Kubelist Podcast, a show interviewing project maintainers for open source projects with a focus on CNCF sandbox, incubating, and graduated projects. Hi, I'm Marc Campbell. Together with Benjie Groot, we publish the Kubelist newsletter dedicated to Kubernetes and the CNCF ecosystem. I'm the founder and CTO at Replicated, where we enable software vendors such as HashiCorp, Puppet, Harness, and many others to operationalize and scale the distribution of their modern on-prem software. Check us out at replicated.com. Benjie is the co-founder and CEO at Shipyard, where they enable teams of all sizes to build, test, and deploy faster and more reliably via their ephemeral environment management platform. Get started with ephemeral environments at shipyard.build. The Kubelist Podcast is brought to you by Heavybit, the leading investor in developer-first startups. For more information, visit heavybit.com. If you're interested in being a guest on this show, or you would like to suggest a project, find us on Twitter at ReadKubelist. Finally, sign up for the Kubelist newsletter and read previous issues at kubelist.com. On this episode of the Kubelist Podcast, Thomas Graf, CTO and co-founder at Isovalent, joined us to talk about eBPF and Cilium. Thomas started off with one of the best descriptions of eBPF that I've heard for anyone who needs a quick background. He then talks about the origins of Cilium and creating the project in the open. Benjie and I took advantage of all the time we had with Thomas to learn as much about eBPF as we could. Thomas spends some time discussing the current state of Cilium and the Hubble projects, and then talks about what's possible with the projects today. Thomas was a great guest and makes this complex topic very approachable. Enjoy. Hi there. As you just heard, we're here with Thomas Graf, CTO and co-founder at Isovalent, to talk about Cilium and eBPF and probably lots of other cool stuff. Welcome, Thomas.
Thanks a lot for having me. It's great to be here.
Great. So we often like to get started by learning a little bit about the path you took to get to your current role, how you got to working in this technology. Will you give us a quick look at your background?
Yeah, so I have a very low-level background. I started out as a kernel engineer, spent 10 years at Red Hat doing low-level networking, kernel development, working on IPv6, IPv4, routing, quality of service, all the nerdy low-level networking, and then got more involved into security. But still in the kernel space, I was involved in IP tables, the audit subsystem, LSM, initial namespacing that are now powering containers. Did a couple of years at Cisco during the OpenStack days. And then we got heavily involved in Open vSwitch, which drove the software-defined networking age from an open source perspective. And then ultimately got into eBPF, which brought me to Cilium and the eBPF development that we're doing today. So I have this open source heavy, kernel development heavy background.
Awesome. And I can't, of course, forget, Benjie here as my co-host. Hey, Benjie.
Hey, Marc. Yeah. Wait to say hi until after the first question, but that's okay. Hey, guys. Thanks. I'm really excited to have Thomas on. Everyone knows I'm kind of a little bit of a EBF fanboy, which I might be the only one that's a fanboy of that, but I am very excited to hear about this stuff. So, Thomas, thanks for coming on. I would love to hear just a little bit more about, just since we're here, how did you get excited about open source? What was your first sniff that got you really going on it?
Yeah, I don't quite remember what year it was, but I got a set of floppy disks with Linux on from a friend, and a friend told me, hey, this is awesome. This is something that you can toy around with, and you get this operating system. And by the way, it's free, and there's this massive open source community around it, and it's evolving very, very quickly. I'm not quite sure what it was, whether it was Slackware or something else, and that got me hooked onto Linux. I was not doing a lot of software development yet. I essentially just came out of gaming and using computers for that sort of thing. Got hooked onto Linux and then started doing software development. And initially, I think very similar to how others have been doing this, writing small little programs. For example, together with friends, we wrote an IRC server, or we wrote a small audio streaming client and service and things like that. And then by accident, I actually got into kernel development. That's quite a funny story. So I was doing, for one of my university classes, I was getting involved in learning IPv6. And in order to learn and really understand it, I wrote this small little chat application which was using IPv6 destination options. So that's quite a deep or very specific extension of IPv6 that allows to essentially insert random headers at the network level into the IPv6 protocols. And I was using that to essentially write a chat application where you could send messages back and forth that would then get the message injected into those IPv6 destination options. And then for some reason, that application did not work. And I read the Stevens book over and over again, which was documenting these system call APIs, and I could not identify the mistake. And at some point, I was really sure that my code is right. The Linux kernel is doing something incorrectly here. So I started digging and digging and digging, and eventually ended up in kernel source code and actually found the problem. And I found like some calculation around setting the length of those destination headers was wrong, was off, which is why my app did not work. And I ended up submitting a kernel patch. The patch was completely wrong, and people gave me feedback, and I corrected it, and eventually the patch got in. But that's how I got involved in the kernel development, and it opened up my eyes in terms of, it's possible to do kernel development, and I can work on something that then gets installed in millions of devices, and everybody can use it. And that, I think, was very attractive and got me completely hooked. And I also truly believed in open source would improve, I think, the ecosystem and would provide something that we can all build on top on.
That's awesome. There's lots to unpack there. Like I love, digging in, working on code, and then saying, my code is right, the kernel is wrong. And then we've all thought that at times, but you actually validated it and got a patch merged in. And most of us haven't gotten that far. It's too, most of us end up finding out, no, I'm wrong.
Yeah, no, I've thought that every time, and I'm always wrong. I think there was one Yahoo Sports API I tried to do something with maybe 15 years ago that actually was broken, but pretty much everything else I've ever done was always my fault. So that's an intimidating story, frankly, that you got something into curl. That's really cool.
It took me weeks to actually convince myself that my code is really right. Obviously, I was in exactly the same position. It must be my fault. It must be my fault. It must be my fault. But eventually, I think that's also what I learned doing more than 10 years of kernel development. Kernel code is really high quality, but it also has bugs, right? Like every other software. It's just the consequences are super high, which is why we try to do everything we can to keep the quality high. At the same time, it's also just humans working on it.
So wait, have you met Linus?
Yeah, absolutely. Yes. I'm not sure whether he would remember me. I definitely remember him. He was very approachable early on. He was at conferences, at Kernel Summit and so on. He's a normal human being like everybody else. I think he's very, very opinionated, of course, right? And I think that's also needed. I think he's also grown quite a bit as a leader overall, but he was awesome to deal with. And I think from an outcome perspective and the type of community he has created, it's fantastic. I would definitely do quite a lot of things differently in terms of how to treat everybody. But I think that's a topic or a subject that's been well.
Yeah, I didn't mean to dive into that too much, but speaking of fanboy, I've been a big Linus fanboy, and I had an idea, by the way, that I'm throwing it out to the community. I think Linus should get a Nobel Peace Prize for Linux. I'm sure that's going to upset a bunch of people, but I honestly think that Linux is probably the most impactful humanitarian thing of all time, or one of them. And so it's just kind of cool to talk to someone who was working on this back in the day and remember stuff. Way off topic, but I just really cool that story. And I can't believe I'm talking to a curl contributor. I've used your code thousands and millions of times, and my company, we abuse you for all kinds of stuff. That's really cool. All right, well, we can move on to a little bit more modern day stuff, but I feel like we could pick your brain about all the contributing. Marc, do you have anything else? Because this is a pretty interesting conversation. I don't want to.
No, I think, that background is awesome. Let's fast forward all the way to today. Now, Thomas, you're the CTO and co-founder of a company called Isovalent. Can you tell us what does Isovalent do?
Isovalent is the company created by the people who have created the Cilium project, and I'm sure we'll talk about the Cilium project quite a bit. So it's essentially a company that brings eBPF into the hands of enterprises. So eBPF was kind of the next logical evolutionary step for us networking and security people on the kernel level. And we were sure that this is the defining technology in how we would define and provide infrastructure for enterprises and customers and essentially everybody using or investing into software-defined infrastructure. And as part of that, we created the Cilium project. And based on the success of that, we have founded a company around it and growing very, very successfully now.
Before we dive into Cilium, I feel like we've got a kernel contributor on. I would love for you to explain a little high level, but feel free to get a little deep level on what eBPFs are. Imagine that I have no idea what that is. Yeah. I'm not the only fanboy, apparently, of eBPFs. But will you explain high level and then feel free to get a little detailed there? Just what is eBPF? Like, what is going on here?
Yes. So I think, as you mentioned, I think one aspect of open source is, and Linux is, it's driving all the devices. Like it's millions and millions and millions of devices, from like Android to set-top boxes to mainframes to laptops to servers to cloud is built on Linux and so on, which means that whatever is part of the Linux kernel is available everywhere. Also, the Linux kernel or the operating system has a lot of control. It can see everything. It can control everything. It's being used to provide networking and security. And if you have a piece of functionality in the Linux kernel, it's literally available everywhere. This is why it's super interesting to do kernel development. The one big downside of the Linux kernel or operating system development in general is that everybody wants a very mature operating system. Nobody wants their operating system to crash, which is why kernel development has traditionally been very slow, very difficult, very, very challenging to find consensus, and also why typically nobody is consuming the latest bleeding edge kernel versions. The times of compiling your own kernel and rebooting the machines are mostly over. Right. And this actually created a challenge. And I've lived through that challenge as part of my work at Red Hat for years and years and years, where Red Hat sold an enterprise distribution at the same time tried and wanted to be or kind of create innovative products. So whenever we did kernel development work, we wanted to get that into the hands of users as quickly as possible, but our customers were not interested to run the latest and greatest kernel. And this created this kind of conflict. And what eBPF provides is a way out of that. To describe eBPF in one sentence, I would use what JavaScript is to the browser, eBPF is to the Linux kernel. So if we think back kind of how web browsers evolved, web browsers are also an incredibly complicated piece of software, and it's very hard to change a web browser. But there was a time when, let's say, if you think back 20 years, there was a time when where we were required to update our web browsers frequently to access certain websites because they may need HTML 4.1 or like some other more modern version of one of the web protocols, and you had to upgrade your web browser continuously. And JavaScript and other sandbox languages changed that forever, and all of a sudden, a whole set of innovation was unlocked that eventually led into huge applications like Google Suite, Twitter, and other web apps to be created. And that's because JavaScript enabled a sandbox program to run part of the browser and to let application engineers or developers to write code that would then run as part of the browser in a secure manner. And that's exactly what eBPF does as part of the Linux kernel. It allows application developers to run programs safely, securely, and efficiently as part of the Linux kernel to drive innovation, to add the capabilities to the Linux kernel, but without compromising the security model of the Linux kernel, without risking to crash the Linux kernel. So this is what now essentially enables a very similar wave as we have seen with programmability around web browser. We see that same wave around programmability of the operating system.
That's a great description, like probably one of the best descriptions of eBPF I've ever heard. So it allows me to write code. I can keep the mature Linux kernel that I'm running. I don't have to update to like you mentioned, compile or like the bleeding edge version of the kernel. So I have a stable operating system, but eBPF provides a way for me to like extend that with new functionality while keeping the maturity. So like, I'd love to talk about like that isolation, right? Like some of the code that I'm using to extend it may not be the most secure or the most mature code, which is why it's not in the Linux kernel. How does eBPF like create that sandbox and that isolation so that I'm not risking the integrity of the entire system when I'm extending it?
Yes, so eBPF is a bytecode language, very similar to Java would look as well. So there's a generic bytecode language, which makes it portable. And it's actually, given that Microsoft ported eBPF to Windows, it's not even Linux specific anymore. You essentially have eBPF programs that you can run on x86, on ARM, AMD, but also on Windows kernels as well, right? So you have this generic bytecode language. This describes what the program does. You can then load this program, and it will go through two steps. Step number one is the verification. And this verification will look at the program and will analyze what the program does. It will look at all the different branching options that the program has, and will ensure that every single possibility that this program can take is safe to run. That's a fairly complex operation it performs, and it is limited in what it accepts. So you cannot load programs of arbitrary complexity into the kernel. There is an upper limit on kind of the amount of complexity, the number of branches and conditions, and so on. It's also not allowed to, for example, have so-called unbounded loop. It is possible to loop in eBPF programs, so you can essentially do the same operation over and over again until some condition is met. But it must be guaranteed that this condition is eventually met. That's the bounded part. So you can, for example, loop based on a value that is written somewhere in memory, but this value needs to be guaranteed to be within a certain range. It cannot be arbitrary. And then the last piece is it's not possible to just call into arbitrary other parts of the kernel, which a kernel module could do, but that's risky because if that call is invalid for some reason, it will crash the kernel. Instead, you're essentially leveraging an SDK or an API, very similar to how a Java or a Golang program would do this. You're using a library, and this library, this API, is stable. It's stable across kernel versions, which again actually not only guarantees safety, it also gives us portability. So we can run eBPF programs across different kernel versions as well. And then the last piece is there is a just-in-time compiler, a JIT compiler, which will take the generic bytecode, which can run on any architecture, and will actually translate that into x86 or ARM or some other instruction set that your CPU actually runs, which means that even though you have this portable bytecode language that's generic, the actual runtime efficiency is at the same or is at the same as efficient as if you would recompile and reboot your kernel.
So ultimately, you're basically getting kernel level execution time with a few limits and kind of safety guardrails for you. And so you can do some crazy stuff. Is that very, very simple way of saying it?
Yeah, I think sometimes the limitations are, I think, overestimated. So it's possible to do fairly complex tasks. For example, we have built an HTTP2 parser, which parsing HTTP2 is not simple. It's a fairly complex protocol. But it would also at the same time be wrong to say, I can bring my big legacy application with millions and millions of instructions and I can just run that in the kernel. eBPF is not a general purpose runtime that can run any code. You need to write eBPF programs specifically and within the constraints of eBPF, but you can do fairly complex tasks. That said, I think eBPF, and that's what's unique about eBPF and what it differentiates from something like, for example, WebAssembly. eBPF has been specifically built to run part of the operating system. Its purpose is not to host or run arbitrary applications. You can do that in user space. eBPF is built to extend the kernel. So you bring use cases and you provide functionality that makes sense to run as part of the operating system, not an arbitrary program.
Can you just give me an idea of maybe the speed increase by running this in the kernel versus, the old it's 10,000 times slower to run something from memory versus hard disk and then 10,000 more for memory to L3 or whatever. Is there a kind of a number of how much faster this can be?
Yeah, absolutely. I think the real power of eBPF is its closest relationship would be it's very similar to building edge workloads or building edge clusters, right? So you want to run whatever service you provide, whatever logic you need to provide, you want to run that as close to the data or where the data resides as possible. So that could be as close to the hardware as possible. Like if you look at use of eBPF to provide load balancing, it can be 10x, 20x faster than a pure, even an in-kernel software-based solution like IPVS. I remember when back in the days, Facebook came out and said, hey, world, look, we have replaced our IPVS load balancing with eBPF load balancer, and it's 10x faster. And the world was like, holy, what's going on here? Like that rarely ever happens to get like a 10x improvement. Or we have other examples where we are using eBPF to run as close to the application as possible. For example, we're using eBPF to do HTTP2 parsing, and we're doing that at the socket level, or even when the application is talking to the SSL library, and we look at that data portion, like very, very close where the actual data is. And there's lots and lots of use cases there. So instead of getting the data to some centralized piece somewhere in the middle of the kernel, we can run the programs closest to where the event or where the source of the information is. And that can be close to the hardware, or it can be close to the application. And that can have massive gains because we don't have to inject something, or we don't have to reroute data. We don't have to reroute network packets. We don't have to rewrite, for example, even payload of a file access. We can run the logic, whether it's visibility or filtering or authorization. We can run that where the data actually resides. And this is why eBPF then drives use cases around networking, security, both network security and runtime security, audit, monitoring, application monitoring, performance troubleshooting, and so on. Every time we want to be close to the application, eBPF becomes interesting.
Okay, I have to say something though. First off, this is an amazing description. You've used JavaScript, you've used the JVM with bytecode. I'm going to throw out, to me, I've always thought of eBPF, and tell me I'm wrong here, by the way. This is not that I'm right, but I think of it as like the FPGA of programming. It's like we're like at the hardware level type thing. Does anyone else get excited by, like, remember when we were in computer science school and FPGAs were the future and it's cool? No one? Field programmable arrays?
Absolutely. I think it's not bad because there's a lot of truth to it, right? I think not everybody will want to see it that way, but in particular from a performance gain and from a amount of difference it can make, it's absolutely this. And then there is another element which combined that raw power. I think what you just said describes kind of the raw potential from a power perspective. But then there's the other element, which is equally important, which is eBPF is often the glue. So the kernel can do a lot of things. It has a lot of capabilities and grown over years and years and years and years and years, many, many, many layers. And we want to essentially pick what functionality we need. But we may not actually want to take the regular path through that, like layers and layers and layers and layers of kernel functionality. We essentially want to glue pieces together and establish shortcuts that have not been established before.
That's great. That's a great description of eBPF. And what I'd like to do now is talk about Cilium, right? Cilium is the open source project, like wildly successful and popular open source project in the CNCF that your company Isovalent created. Can you tell us, what does Cilium do?
So Cilium brings all of that powerful eBPF technology into the hands of the cloud native user base, right? So eBPF is super low level. It's targeting kernel developers, and it's primarily been used by companies like Facebook and Google and Netflix with own kernel teams. But it's not a technology that you want to consume in its raw form, right? You essentially need kernel developers to use it properly. So you're reliant on having projects leverage eBPF, and Cilium is bringing eBPF to Kubernetes, to the cloud native world to solve networking, network security, runtime security, observability, and most recently service mesh functionality as well. So we're trying to bring and solve as many cloud native use cases where eBPF is a great fit, and essentially hide the eBPF pieces as much as possible, but bring all the powers to the users.
So that's a lot of different topics. Let's break them apart, I guess. Let's start with one by one. Like, you want to hide the eBPF complexity and functionality. So at a high level, how do you do that? Are you creating best practices policies? Are you creating a DSL so I don't have to write code that compiles into bytecode? Or how does Cilium actually perform that?
Exactly. So what we are doing, we're taking Kubernetes objects such as network policy, Kubernetes services, or gateway API, Kubernetes ingress, which is describes the intent that the user is describing. And then we're using eBPF to most efficiently implement that. And because of the programmability of eBPF, it actually allows us to build a lot of great tooling. So not just have a very efficient implementation of what is needed, whether this is a network policy or whether this is providing Kubernetes networking or Kubernetes ingress or provide open telemetry visibility. It's also allowing us to essentially build troubleshooting tooling and day two operations, observability, dashboards in a way that are appealing and helping users as well. And while kind of hiding the implementation detail of what eBPF is, I think to compare this, it's very similar to what Kubernetes is doing with namespacing technology, right? Most Kubernetes users do not know how namespaces work as part of the Linux kernel. It's the foundation that allow for the isolation and the resource control of containers. But most Kubernetes users don't really understand those lower level details, but it's what unlocked to even build Kubernetes as a platform, obviously together with the container runtimes.
Right. So it's like literally just as easy as like I get the benefits of Cilium. I don't need to be like an application engineer. I can just like I get the power of Cilium just by installing Cilium into my cluster. Exactly.
So I think in many, given the popularity of Cilium, in many cases, you are already using Cilium. You may not even know it. For example, if you're using GKE or Antos or EKS Anywhere, DigitalOcean, they're already using Cilium under the hood, and you will be using it. And in a lot of situations, you can actually just tap into it and, for example, benefit from the observability data that Cilium provides. We have a layer that's called Hubble, which is our observability layer, and it provides visibility into a lot of different layers. For example, all the network communication that is ongoing, like who is talking to whom, please measure the HTTP latencies, show me when network policy is denying some traffic, or show me the amount of traffic volume between cloud provider regions or between availability zones. All of that can be looked into, and Cilium exports Prometheus metrics and essentially flow logs via FluentD and via OpenTelemetry traces. And users can benefit from that and build dashboards or feed data into an SIM and so on. So in a lot of cases, Cilium is already there and then can be tapped into to extract data that's useful for platform teams, for application teams, and so on. And I think the other aspect, I think, is the security angle, which is enriching and empowering security teams with the required visibility. And that then goes more into the runtime side as well, where we benefit from eBPF's ability to not only understand what's going on the network level, where Cilium can see every single network packet that is being transmitted or received, but it can also see all the system calls that are being made. It can see every time a process is changing namespaces, or every time a process is increasing or escalating capabilities, or every time a process is executing another process, and so on. And we can combine all of that information, all of that observability, and provide a lot of insights for security teams as well.
So Cilium is really providing like that, like kernel integration. It's not trying to be the single pane of glass. It's not trying to be the dashboard or the monitoring, the observability tool. It's really trying to collect the data, allow me to pass that into whatever tool in the scenario that you were just describing that I'm using. And I want to actually like have alerting and monitoring and instrumentation and everything on there.
Yeah, absolutely. So we feed into typical open standards, whether it's Prometheus, OpenTelemetry, FluentD logging, and so on. And we implement open standards in terms of user intent, whether it's policies, services, service mesh, and so on. So what we're interested in is to essentially glue together cloud-native standards, whether it's on the networking connectivity side, observability side, security side, and provide the best possible portable implementation of that using eBPF, because we believe eBPF leads to a highly performant implementation that also gives a lot of visibility while doing so. I think this sweet spot has been what makes Cilium so popular, is that we're not only incredibly fast and scalable at doing things, I think we power some of the biggest Kubernetes clusters, but at the same time, we also provide a lot of visibility that used to be incredibly expensive to get. And that combination allows to operate at speed, at scale, while still having a lot of visibility, which is required to operate a complex system such as Kubernetes.
How long has Cilium been around? How long has this project been going?
We started Cilium 6 years ago, and we didn't have this open sourcing moment. We actually started in public. Like the first line of code ever written was already public. So it literally like it's been 6 years since the first line of code was written. We were not part of the CNCF Foundation in the beginning. We actually decided that we want to have a very pure feedback from the user base. So we actually did not want any free marketing from that perspective. We wanted to have Cilium succeed on its own in a pure open source setting first. And then when it became clear that yes, Cilium is what users want, like more and more Kubernetes distributions simply including or even pre-installing Cilium, like the user base growing and growing and growing, that's where we decided now it is time to actually donate and move it into the CNCF.
You talked about creating the project, the first line of code was in a public repo. Like that's not as common as you actually think. A lot of open source projects were created as private projects. And then, once it was ready for like a V1, cleaned up, like in good, then the maintainers will flip the switch and make it open source. I love that creating it just as public and, like it's not good at first, right? It's not functional at first. You don't have documentation, but you have to start somewhere and really showing that journey, showing that path to other engineers, other software developers to show that like this is how software is written. Like that's fascinating. Would you do that again if you could?
Absolutely. And I think it's the best way to make sure that you align with your user base and that you learn quickly and early. But it is more effort, right? It is a lot more complicated. Essentially, you need to keep documentation up to date from day one. You need to convince users to provide feedback. You need to listen to them. If you don't listen and react, they will move off, right? But this means that you are aligning early and you are sure that the open source project that you're creating is meeting a demand, and you can then monitor that demand and act accordingly. I see a variety of open source projects that have this open source day, and then it's a bit hit and miss. It can be a great hit, but what if it is a miss? Yeah. You get like this one big splash, and then if it's a miss, the project is almost dead. It's really hard to then keep it up because from an expectation perspective, you're like everybody's expecting the project to now really, really succeed. If you start small and grow kind of year over year, you get the feedback early and you know whether you are on track or you're not on track. So I would recommend to everybody, if you have the time, if you are in a situation where you feel like you have a strong team to execute on the vision you have, go public, go open early, benefit from the massive feedback you get from the open source world. I think this is the most undervalued aspect of open source. It's this exposure. Linux would never exist without that early exposure. I think if Linux wouldn't have published a very, very early version of Linux early on, Linux would never have gotten where it is today.
Yeah, exactly. It's okay to be embarrassed in the early days. Like, I mean, thinking about Cilium, right? Like eBPF today is still, relatively new. Like it's the more and more adoption of it. But I got to imagine 6 years ago, eBPF is not a term that, was talked about on podcasts. It wasn't like a common term. You have this brand new open source project. It's not, telling folks it's okay. This immature, unbattle tested project that has a few hundred stars on GitHub, install it. It's going to interact and like run kernel level code and intercept Linux kernel calls and things like this. Like that had to have been a high bar in order to like get people to start adopting this project initially and build that trust with the end customers.
Yes, and I think that's the right way to do it. You will find early users, and they will be aligned, and it's on the open source project to identify, okay, these are users that are leading the way, and they are doing what others will be doing at a bigger scale several years later on. The first version of Cilium we published was incredibly extreme. It was IPv6 only, and it was essentially designed from scratch for like massive scalability. We looked at like what would we do to run like 10 million pods? How would we design to account for that scalability? We looked at what's now called service mesh in terms of layer 7, visibility, layer 7, enforcement, all of that. So we defined pretty extreme goals and then actually toned it back from there. And now we're seeing a lot of these initial design goals that we have set are now actually becoming the standard. And it's incredibly rewarding to see that what we now see as common usage pattern around IPv6 clusters, multi-clusters, bigger scalability, identity-based security, all the core principles we have built in the first version of Cilium are now becoming the norm around the cloud-native era as well.
I mean, that's really cool. We have a lot of listeners that, are looking to start contributing, but I bet there's a few that are like, you know what, I'm going to write open source Doom on eBPF. How do I get started? Okay, bad example, but how did you jumpstart the community? Because it's one thing to say, okay, do it in public, but if a tree falls and no one's listening, like what's happening? Like obviously you had some experience with contributing to the Linux kernel, and you were at Red Hat and all that stuff. But what were some of these early successes? How did you get people, when you were doing it in the open, to actually take you seriously and to start giving that early feedback that was obviously so valuable?
So one of the initial really big milestones for us was Dockercon in 2016, which was the first time where we had like a really big conference talk, and we essentially described and demoed Cilium for the first time, and everybody was just learning about containers. At the same time, there was still kind of most solutions from a networking perspective were just the ones that existed before from network virtualization that were created for OpenStack. They've just been repurposed for the age of containers. And there we went and actually showcased something that is very different and targeting a use case that most people were not aware of yet. Like, you will be running at larger scale, and you will think about not only network protocols, but you will think about application protocols, and you need identity, you need like authentication instead of just segmentation and so on. And we used, I think, others that were further along as examples. So I think common examples would be Google and Facebook and Netflix and Twitter that have been using more modern patterns already. And we were essentially designing off some of them as well, in the belief that the wider set of enterprises will eventually get there as well. And that's obviously a pattern that we see very frequently, that enterprises are essentially, with a lag time of 5, 6, 7 years, doing things maybe not quite to the same extreme levels, but like moving towards a similar direction as the hyperscalers do as well. So we were not without signal, but we were not, or the set of users that would eventually end up using Cilium did not exist yet. And I think that's always the challenge. If you want to innovate around open source, you need to be ahead of the curve. At the same time, you need that user feedback. You need that feedback channel. And I think open source conferences can really help to find early users and get into a conversation with them as well. So I think Dockercon, Open Source Summit, and then KubeCon later on were incredibly helpful. I remember going to KubeCon Berlin, and we had a small booth there from a Cilium project perspective, and we got overrun. Like, everybody was interested in this. Oh, I need visibility. I need better networking. Like, it was an exciting time, and we got a ton of amazing feedback in terms of what we could be doing better, what is meeting demand, what is not meeting demand, and so on.
All right, this is just such a great example for the community to follow this project. But let's switch it back a little bit to Cilium itself. I have a question, and that is, because I've done a little bit of eBPFing, as you know, as the number one fanboy. Mm-hmm. So let's talk about overhead, and let's talk about how you get installed. I'm assuming a stateful set, but just talk to me if if a Kubernetes operator today, and I'm like, I want to start taking advantage of this stuff. GKE does it. I'm going to do it. How do I install it? Like, it's pretty simple. I take it, but also, I want to understand overhead, because I feel like overhead is the one a little bit like elephant in the room a bit. Like, how much does running these different things cost me on my raw compute side and memory and all those other things?
Yes. So installation is very simple. Cilium comes as a daemon set. It essentially runs an agent on all your Kubernetes worker nodes written in Golang. And this agent will connect to the Kubernetes API server and will receive the policies, the services, all the intent it has to implement. This Golang user space agent then interacts with the Linux kernel or the operating system to install the eBPF programs that will perform the actual required operations. So, for example, perform the networking, perform the load balancing, implement kube proxy functionality, extract visibility, set up multi-cluster, enforce runtime security policies, and so on. There is also an operator or a leader that gets elected, which is the minimal control plane. In general, everything that Cilium does is backed with custom resource definitions in Kubernetes. So Cilium does not come with a massive control plane on its own. It does have one component which is centralized using Kubernetes as its leader election. And that's simply a deployment that can run in a highly available version. Cilium can also be run on non-Kubernetes worker nodes as well. So you can actually run Cilium, for example, automate it with Puppet or Ansible or Terraform or some other automation framework, and actually install it on a virtual machine or on a metal machine and make that machine part of the mesh as well. So eBPF is not Kubernetes or container specific in any way, so you can actually benefit or bring the powers of eBPF to outside of your Kubernetes cluster as well. And it's actually what we see a lot of users do. They want the connectivity that Cilium provides, but they want that for more than just a containerized application. They want the Kubernetes workloads running in the cloud, for example, maybe with an OpenShift cluster running somewhere, and then they have a couple of metal boxes with a database and then a fleet of EC2 VMs running some applications, and they won't connect all of that together. They want security control across all of that. And eBPF is an amazing technology to get that single platform going where you can do all of that in a portable, in a universal way. So on Kubernetes, as simple as a daemon set. Outside of Kubernetes, it typically takes some sort of automation framework to install the Cilium agent, which will then orchestrate the eBPF layer. In terms of overhead, the overhead on the networking side is incredibly minimal. And I can tell a story which is kind of funny. We did a lot of benchmarking, and you can find all the networking benchmarks we have collected on Cilium.io. One of the numbers was surprising to us, and we actually measured it over and over and over and again because we believed it was wrong, because we measured that a pod talking to another pod on two different nodes was faster than the nodes talking to each other directly. I was like, oh, this can't be true. The nodes like this, there's less complexity involved. Why should containers be faster talking to each other than the node themselves? And it took us several days to realize that, because with eBPF, we were essentially bypassing the IP tables or net filter layer on the host. The pod-to-pod communication was quicker. So the container networking that we are doing as part of Cilium takes less time than even an empty IP tables rule set on the host itself, which was surprising. And I think it shows some of that gluing power that we talked about earlier. It's not just about the raw potential on how fast eBPF can run. It's also about essentially removing part of the system that you don't need. So if you don't need IP tables, let's bypass it, right? If you don't need, for example, some sort of additional visibility layer, let's bypass it. If we don't need the network injection and we just need to copy data, let's do that. I think it's allowing to rethink how to do things and actually cut overhead out. When we measure overhead, where we have overhead, it's typically around observability. And the amount of overhead there dramatically depends on how much observability you want and in what form. So it's obviously a lot more efficient to collect a metric and increment a counter or create a histogram than it is to essentially create an event or a flow log for every single packet that is being forwarded. Cilium can do both, and depending on how you configure it and what level of aggregation and filtering you can configure, the overhead can be from point something percent to 20%. And often it is actually not necessarily the kernel level data exfiltration that we do. It actually comes down to boring JSON encoding and other things popping up in the performance profile, because that's very expensive. So we get all of the observability, but then we have to do JSON encoding and write it to disk, which is very, very expensive. So not an easy answer, but I think the short answer is that depending on what you need, you can heavily optimize it and get it down to lowest level. We're actually running Cilium in some stock exchanges with lowest of latency kind of needs without any issues. So I think definitely from a potential perspective, it's fully capable to run in highly low latency, high performance environments.
Wow, it's just, every time I dig into the eBPF stuff, I just am always like, it makes Boolean fries. It does everything for me. It's really cool. Speaking of which, you mentioned that you guys are adding a service mesh to the Cilium ecosystem. Can you talk a little bit about that? Because I feel like that really dovetails well with what you were just describing with the lack of latency, or whatever the right term is.
I think overall, the Cilium feature set and the design goals actually align really well with service mesh. Like, it's being close to the application, it's understanding the application, it's understanding application protocols. So not just like keeping or staying at TCP, but actually understanding HTTP. And instead of understanding a TCP latency, understanding the HTTP request response latency, like that, like elevating the level where we argue and where we provide visibility. So there's a strong alignment around that. Historically, we have not called ourselves a service mesh because we weren't able to do all of the service mesh functionality. Things that we have not done in the past were things like layer 7 traffic management, retries, and circuit breaking, as well as MTLS. But we have provided, for example, HTTP visibility, network security, multi-cluster, load balancing, sort of like canary rollouts, and so on. So because we did not have a full integration, or like not the full feature set, we actually did an integration with Istio. So the first service mesh kind of offer we had as a Cilium project was to have a native Istio integration where you can run Cilium and Istio together. Istio is one of the more successful, more popular service mesh projects that are out there. And we've done a variety of things such as accelerating Istio, removing the unencrypted payload aspect of a sidecar, and like a variety of optimizations where we can help a Istio or a sidecar implementation. And that was great, and a lot of users were successfully running that. And then over time, more and more users approached us and said, it would be awesome if you can help us like get to a more efficient service mesh. And there's a couple of problems that we would like to solve. First of all, if possible, we would like to avoid running a vast number of sidecar proxies. So like most service meshes today implement service mesh functionality with a sidecar model where they essentially run a proxy for each pod. And this proxies all the traffic and essentially funnels and provides all the functionality in that sidecar proxy. So if you run 1,000 pods, you will need 1,000 sidecar proxies. And they asked us, can you do something about this? So we started working on it, and we started out with implementing a variety of functionality purely in eBPF. So I mentioned we have implemented an eBPF-based HTTP2 parser that is able to provide tracing data completely transparently without running any proxy at all. And you can give application teams like a golden signal dashboard and show latency numbers with no impact, or like a minimal impact. I think the override is less than 2% on the overall latency, like really, really low overhead, but with the same functionality. But that's only the visibility portion. It cannot do any traffic management. It cannot do any load balancing. For those use cases, we still go to a proxy. And this is where we go to the Envoy integration that we had for years as well. As I mentioned, we actually went to be layer 7 aware almost since day one. And we've always integrated with the Envoy proxy, which is another CNCF project, which provides things like HTTP, gRPC, and now also things like Kafka parsing. And we've been using Envoy in a per node configuration to actually get those layer 7 services very successfully. So we have brought that integration as well and call it Cilium Service Mesh. So Cilium Service Mesh today is a combination of eBPF-based service mesh functionality, Envoy proxy-based functionality that is not a sidecar, and a new model of doing MTLS that does not do the authentication as part of the payload, but actually does that separately. It gets fairly technical, but that has a massive benefit that we can run MTLS and make it compatible with any network protocol. So we can support any network protocol while still relying and still benefiting from the mutual authentication part of TLS. So essentially, users are driving us to solve some of the service mesh pain points that exist today. With a clear ask that please don't reinvent the control plane. So please support Gateway API, SMI, Istio, Kubernetes Ingress, Kubernetes services, but please optimize the data plane and get us to a more efficient version of the service mesh data plane. I think there have been some tweets recently about, hey, I'm using 20% of my compute just for service for my sidecar proxies. That's definitely something that users want to avoid, and that's the problem we are looking to tackle, while essentially providing that universal data plane that is compatible with a variety of different service mesh control planes.
Yeah, I mean, speaking from maybe 3 years ago maybe 4 years ago, I don't even know. Well, a while ago when I first turned on Istio for the first time, I think it was V1, maybe not even V1. It was using 200% of my compute, so that was quickly a problem. It's good that it's down to 20%. Honestly, you said you could do MLTS on any protocol. Did you say that? Did I hear you say that?
Yeah, so this is, I think we're all using TLS every day, right? When we, let's say, go to our online banking app, we're using TLS to secure that connection. The browser does it for us. And TLS is fantastic for the internet, right? Where TCP and QUIC are the primary protocols we use. Unfortunately, enterprises use a vast variety of different protocols as well, some of which we have never heard of. And as they bring more legacy, more traditional enterprise applications to the cloud-native world, they essentially need service mesh connectivity and the values that a service mesh or like a connectivity plane provides, but with the compatibility for these older network protocols as well. And the way we do that is by separating the connection and the network protocol that actually carries the data from the authentication itself. So instead of making the authentication and the transport of the data as one connection, which essentially limits it almost exclusively to TCP, we separate the two. So when one service wants to talk to another service and it's using a legacy protocol, Cilium will hold up the data, authenticate the services with each other using MTLS, and once that authentication has succeeded, it will allow the data to flow. And it can then use IPsec or WireGuard to encrypt and authenticate the data independently of that. And this has one massive benefit. Aside from supporting any network protocol, it also separates the authentication away from the data path. HTTP is incredibly hard to parse, so proxies have typically been vulnerable to vulnerabilities quite repeatedly. And by doing TLS or MTLS as part of the proxy, we need to share the key, the certificate, the secret with that proxy. So if the proxy gets compromised because of an HTTP vulnerability, the key gets leaked, the key gets lost. By essentially moving the authentication part out of the proxy, out of that vulnerable data path part, we're actually improving the security posture as well.
So I want to talk about like the extensibility of Cilium specifically, right? Like eBPF has all this functionality. You're talking about this really cool stuff like MTLS on UDP transmission. If I have Cilium installed, like what can I do with it? Like obviously you talked about network security with Cilium. You talked about like observability and monitoring with Hubble, which are the two main projects here. But like, what else can I do? How extensible is it if I have another thing that I'm like, oh, I just want to do this? Do I have to go write eBPF code to start and just say Cilium solves this problem? I'm going to go solve my other problem. Or can I like write policies that actually like execute code in Cilium?
So for the vast majority of use cases, you will never have to touch eBPF. We do have really powerful users that want to essentially extend the eBPF data path capabilities, but most of these changes actually flow back into the open source project. For example, we have telco customers that are heavily relying on Cilium now, and they're actually extending the data path capabilities by working with us to extend the eBPF portion of it, and then finding ways to expose control over that in a Kubernetes or cloud native way. So think telco 5G with CRDs, where you can bring application developers and give them a user experience and a developer experience that's aligned to cloud native and Kubernetes with the low level latency and throughput and network protocol control that's needed for a telco network. So there are powerful users on that level where they want and need control on the eBPF level. But for the vast majority of users, it's essentially that most of the functionality is already there. And it's mainly about using the functionalities, writing the policies in YAML or in JSON, using Kubernetes objects, or implementing existing standards and extending them. For example, implementing more and more of the Kubernetes ingress resource, or we're now working on implementing the gateway API resource and so on. So it is possible to use eBPF if you want to operate on that level. That's not needed for the vast majority of users.
Got it. That makes sense. And one of the things that, we haven't actually talked about, eBPF, we talked about the performance benefits you get from running it in the kernel. We talked about some of the, limitations you can't have, like what you can and can't do. It's bytecode. But we haven't really talked about probes. And like, that's actually one of like the huge values that Cilium, I'm guessing, is providing inside eBPF, where I can know when this kernel function is being called because like the code is actually running in the kernel.
Yes. So I think observability and troubleshooting ability is what we have underestimated the most in terms of needs when we created the Cilium project. I think initially we started the Cilium project and we focused heavily on the security aspects, and we built better and more secure controls. And then we quickly learned, I think that was a benefit of exposing and opening up early, that as Kubernetes is complex, as the scalability increases with containers, as multi-cloud becomes a reality, this end-to-end visibility and understanding all aspects, essentially from app to app, and understanding where it might fail, what is working, what is not working, is super crucial. So this day two operational visibility, whether it's kind of understanding when is DNS failing, correlating like an HTTP latency with CPU load, or understanding the HTTP error rate, or correlating a network policy drop with an application failure. All of that is super crucial. And what's amazing now about eBPF is because of its performance profile, because it's so low overhead, it actually gives us the opportunity to look at a lot more things at different levels, because it's such at the low cost that we can do so. Some of these things were possible before, but they came at such a massive overhead that it was not possible to actually run any of it in production. So we all know back in the days when we had to reproduce issues like customer issues in a repro environment and then measure and get insights. One major use case that Netflix used eBPF for was actually performance troubleshooting in production systems where the application was maybe not performing as well as it could, and observability was needed in the production level system because the actual issue would only reproduce at scale, at massive use. And we apply the same principles for Kubernetes workloads as well, whether this is load balancing at high speed, or whether this is large scale, or simply even for smaller deployments, just the deep visibility and understanding where does it fail, what is working, what is not working. Is it DNS? Is it a proxy? Is it the app? Is the latency because of the network? Is the latency because of the app? And so on. Like a lot of these fundamental questions can be helped with eBPF and Psyllium.
I mean, I think there's something, I don't know if we've actually talked about this, but it's just, this is such a, I plan to send this episode to a lot of people that have asked me a lot of questions about eBPF. So I'm just going to make sure I get everything in there. But I feel like one of the coolest things about this is like what we're not talking about is like, I don't need to integrate anything into my application to get all these benefits you're talking about.
Yes.
When you say that you install a daemon set, you mean I'm literally, just to be clear here, and correct me if I'm wrong, of course, but I am literally just installing something onto a node or a daemon set or whatever, and I just get all this magic stuff that basically just goes around in a sort of, well, it's safe. I hope it's safe. I don't know. That's always been my anxiety about this stuff. I'm like, okay, it's a little too good to be true always. But it goes around all of these things. It goes to the kernel level, uses probes. So you kind of, you're not polling. You don't have these endless for loops and all these other things. And it just gives me all this observability. It gives me all this ability to like, man in the middle of my own application, basically. Is that right, Thomas?
Absolutely, yeah. I mean, I'm coming from the infrastructure world, so to me, that's requirement number one. So I always take that for granted, but that's 100% true, and it's a massive value. There is no code instrumentation. There is no code injection. There is no redirection. Like, we're looking at what an application is doing. We're looking what is the system doing. We're looking at this not only at the system level, but also in a distributed way. So we can compare the data that we observe on different nodes. And we can even correlate a request as it leaves a node and is being received on another node and correlate all of that together. It's incredibly powerful. It's simply something as an infrastructure engineer, that's always something that was required, and without that transparency, it wasn't an infrastructure solution. But it's a massive value, absolutely.
Does Cilium have something where I can just play back the kernel space or something for the last 10 minutes and put it on some?
We have something that we call Timescape, which is essentially that's getting into our commercial product. That's a time series database based on ClickHouse that can record all of these observability events, like on the network level, on the runtime level, on the application protocol level, whether it's a network policy event or an HTTP request or a system call or a privilege escalation or a process execution, and can record all of these events and collect from all the different nodes and then correlate the information together and build models. For example, we can build this amazing service maps, or we can automatically generate network policy. We can identify certain patterns. To give an example, we can, for example, understand when a container is usually not ever launching another process. So it's a single process container. So it always only executes this single binary, probably statically linked. And then we can understand, on this one occasion, it actually did start a sub process. which is then very likely actually a security relevant incident because maybe the container or the pod was compromised and a stop process was started. So like a lot of can be done with this data that we record, and we can also replay it. So we can actually replay some of the network traffic we've seen. We can even replay some of the runtime behavior that we have seen. So we can replay the file access and so on. So but that's getting into some of the commercial product that we have. But absolutely, I think that's one of the key benefits of eBPF, that because of the low cost, we get a granularity of data that we can then use to store essentially this auditable stream of events that can be fed into a time series database.
I don't forget how crazy it is. There's no application tooling whatsoever. I feel like the eBPF people don't realize how revolutionary that is. At Shipyard, we use Sentry a bunch, and I love Sentry, but like, imagine if I didn't have to do any tooling at all. It's so cool. But let's talk about the commercial product a lot. Like we have people, it's always good to understand how open source projects support themselves, how you monetize, because we want these things, and you guys have obviously been amazing stewards of this project. We want you to succeed. We want this project to live on. So tell us a little bit more about the commercial offering. I think you just told us some pretty cool features, but give us a little more. Give us a little more. Sell me a little bit, just a little bit.
Yeah, so I think, first of all, Cilium is open source, and we completely believe into open source as the best way of doing innovation. At the same time, it's obviously important for our company and all the customers that bet on the technology that we as Isovalent are successful as well, because the technology needs to be maintained. And even though the list of contributors that are coming in from the outside more and more, the list is growing, essentially Isovalent is still fundamental that Cilium continues to grow successfully. So from that perspective, we sell an enterprise distribution of Cilium, which essentially provides Cilium open source in a hardened version and with an extended end of lifetime, a proper security policy like backporting, professional services. And then on top of that, we have a list of features which are enterprise only. I mentioned one of them, which is Hubble, our time machine database. We also have a set of compliance monitoring aspects. Typically, when enterprises want to achieve compliance, some of the visibility aspects there are enterprise only. The HTTP2 parsing, the low overhead one, like this highly optimized eBPF parser, is enterprise only. So we essentially provide enough to be successful on your own in the open source version, and then have optimized versions and additional enterprise specific functionality that is found in our enterprise product.
If I'm an enterprise, what is the coolest feature that I get if I do enterprise?
I think that depends a bit. I think for many, it is the amount of security visibility that you get. So the richness and the automation of all of it, which means that you install the enterprise version, and without doing anything additionally, you can see what TLS, what are the TLS connections ongoing? What ciphers are they using? Is any of my apps using an insecure cipher? I see the HTTP level. I can probe my SIM and, for example, look into cross-scripting attacks into the HTTP URI. I see the entire network layer. I see all the DNS resolutions. I can quickly probe which pods are actually talking to outside of the cluster, which pods are exposed to outside of the cluster. I can then correlate that with, for example, runtime information and identify which pods are listening on what port. In the last 2 weeks, have some applications started listening on a new port. All of these questions that a lot of security teams have, they get immediate answers to that. And without actually installing a lot of different components, they install the product and essentially get all of that observability data neatly covered in a time series database. And even better, that works across all the cloud providers. It works whether it's in cloud or whether it's on-prem, even outside of Kubernetes itself. So I think that's the real aha moment that our customers have is, I get all of that observability immediately at super low cost, and it's multi-cloud aware, it's hybrid cloud aware. And that's essentially what security teams want and need, because a lot of them don't fully understand Kubernetes in all details yet.
Yeah. I know we're starting to run a little bit long and out of time, but like there's one more question that I'd love to hear your thoughts on. And that's, it's kind of a couple of questions in one. Like, what's next? What is the team working on right now in the open source world for Cilium, for Hubble? Or if I'm just like super interested in providing feedback or contributing or running it, like what type of feedback, or how do I get started and involved in the ecosystem?
Absolutely. So I think we have an amazing set of users that are continuously driving Cilium forward in additional networking use cases, whether it is telcos, high frequency trading, multi-cloud aspects, hybrid cloud aspects. But then there's also the complete service mesh space. And I think my prediction is that what we now call service mesh and what we called CNI or cloud native networking, I think this will all become one layer. And users and customers will essentially demand from the cloud native space that I want this connectivity plane. And this should be as efficient as the network used to be. It needs to be completely transparent, but it needs to be close to the application. It needs to understand application protocols. It's no longer enough just to understand TCP and to look at TCP retransmissions as a way of achieving resilience. We need to understand HTTP retries. We need to have layer 7 awareness when we do load balancing, but without introducing a vast majority of overhead and while being aware or while being compatible to the enterprise legacy world as well. And most importantly, while being able to connect and integrate the vast majority of workloads that are not yet containerized, that are not running on Kubernetes itself yet, but where there's a huge demand to bring cloud native principles and concepts to that world as well without having to migrate them. And I think that's what we will focus on the most. Like as this space converges together, we will invest heavily into working with customers to make them successful and allowing the wave that is yet to come to be successful as quickly as possible.
I mean, this is great. I have a whole list of things that I wanted to talk to you about that we didn't even hit, but we're up on time. I'm going to do a little shout out though. The Go eBPF library. I'm pretty sure you guys wrote that, right?
We wrote it together with Cloudflare, so that was a joint effort. But yes, we were heavily involved in this.
So that's just another project for the audience to go check out if you want to get low level with the eBPF or contribute to that possibly. Thomas, I was not being facetious earlier. Like I am literally going to actually send this episode out, say fast forward the part where I talk, but listen to everything that you have to say. This is so informative. I have one last question before we wrap. What is the name of the bee?
It's called EB. We voted on it, I think during the last eBPF summit. So we organize an eBPF summit every year in summer, and this year it will be late September. And as one of the exercises, we named the mascot and we called it EB.
Wonderful. Okay, and that's great way to leave it too. September, there will be a eBPF conference. I will put a link to that in the description. Could not thank you enough for coming on. Thanks, Marc. Thanks, everybody. And as much as this all seems like black magic, I've played with it. We use it. It's great. It all works. I'm waiting for, I don't know what's going on, why this all works so amazingly, but it does. It's really cool. Check it out. And obviously check out Cilium.
Thanks a lot for having me. This was great.
That's all we have time for today. If you're interested in being a guest on this show, or if you would like to suggest a topic, head over to Kubelist.com. I'm Marc Campbell, CTO at Replicated, where we enable cloud-native software vendors to operationalize and scale the distribution of their modern on-prem applications to their largest enterprise customers. Check us out at Replicated.com. My co-host is Benjie de Groot, CEO at Shipyard, where they enable isolated ephemeral environments on every code change for companies of all sizes. Check them out at shipyard.build. This show is brought to you by Heavybit, the leading investor in developer-first startups. For more information, visit heavybit.com. And finally, don't forget to sign up for the Kubelist weekly newsletter and read previous issues at kubelist.com.